This is where I present to you a very simple model based on the tartaric acid equilibria for making all different kinds of wines, and I call it the magic of pH 3.45. Okay, so here we go, all in one place, so that you can understand the different ways of making different wines, all coming from the same starting point. So here's the good old tartaric acid equilibrium that we're all familiar with. You remember that there's a pKa at 3.0 for the first dissociation, and then 4.2 is where the second dissociation is 50-50. So if we look at that graphically, we're saying that there's a dissociation there where the two lines cross, and another one there. And the average of the two, the peak of the bitartrate curve, is pH 3.6, which I consider the great divide between white wine making and red wine making. And we know that right there, that potassium likes to combine with bitartrate as the ethanol rises during fermentation and also is exacerbated by chilling. And we get this precipitate that we're familiar with, potassium bitartrate. We've also learned that if the pH is above 3.6, then the tartrate side of the equilibrium will predominate. And that means that when the reaction takes place, the TA goes down and the pH goes up, which kind of makes sense. However, the weird thing is that if we're on the other side, where the tartaric acid equilibrium is more important, below 3.6, when we cold stabilize, the TA goes down just as it does above 3.6, but the pH goes down. So we're going to take advantage of these two, and that's got a lot to do with how we're going to bring our wines in on target in different styles. Now let's go through a few fermentation rules of thumb. These are approximations. They're going to vary in each wine, but it gives you the idea. The first is that 10% of the malic acid in the juice gets consumed by yeast, and it happens in what's called the transition phase. After the yeast have grown up to 10 to the 8th, they're not going to grow anymore, but now they're going to hang out in the stationary phase and do all the fermentation. When they do that, when they turn that corner, they need to retool a lot of the proteins. So what they need is a fresh set of amino acids that they make from malic acid and something called the Krebs cycle, which malic acid is an important member. And so we get this reduction of malic acid, which lowers the TA a little bit and raises the pH a little bit. Then we have the bitartrate precipitation itself, which will lower the TA about a gram per liter. If the pH is lower than 3.6, this lowers the pH further. And if it's above 3.6, then it raises the pH further. Simultaneously, in red wines, we have skin contact that will raise the pH about 0.2 and about half of that in the first 24 hours. Now, once we've got our fermentation done, there are some cellaring rules of thumb to consider. The first is that if we have malolactic, it will lower the TA by somewhere between 0.5 and 1 gram per liter and raise the pH around 0.1 to 0.2, depending on ripeness. The reason I say that is if we get the grapes really ripe, then we have less malic acid. We'll have less of this effect. In high pH, long aging reds, we have another effect. So we're talking about these big, bold Cabernets and Syrahs where we want to have low TA so that the salivary protein is minimized that will react with the tannin. So there's a reaction that happens only at high pH, and it's very slow, where SO2 reacts with oxygen to give us H2SO4, sulfuric acid. That's a strong acid which completely ionizes, gives us a couple of protons. There's no equilibrium. So we get 2 protons and sulfate, and that can lower the pH about a point, about 0.1, for example, from 395 to 385, while raising the TA only by about 0.5 grams per liter. And that's because sulfuric is a strong acid. It also adds an interesting sort of a phenolic floor to the finish of the wine that's very characteristic of Bordeaux or the wines of Tuscany or the Rioja. Cold stabilization will lower the TA. It varies quite a bit, but let's say rule of thumb about a half a gram per liter. And again, if the pH is below 3.6, that lowers the pH a little. And if it's above 3.6, it raises the pH a little. So we're going to bring all of these elements into the dance as we make different kinds of wines. Let's start with what I call crisp whites that are not going to be taken through malolactic. And as an example, Sauvignon Blanc, let's say we set our target pH at 3.25 and the TA we want at 7 grams per liter. So it's a little bit crisp. We're going to first adjust the must to pH 3.5. And let's say that ends up giving us a TA of 8.5 grams per liter. That's kind of perfect numbers. If we get them at harvest, that's great. If we don't, and our pHs are higher and our TAs are lower, then we're going to add tartaric acid. The rule of thumb is 1 gram per liter gets you a pH drop of about 0.2. It's best to go into the lab and try this in a small sample, take 100 mils of wine and add the corresponding tenth of a gram per liter and see if that gives you that 0.2 pH shift. All right, now how are we going to get there? Well, let's go through the steps. First thing is we have that malate consumption, and that's going to take the pH up a little bit to 3.48, while the TA drops down about 0.3, so we'll call it 8.2. Then we're going to get our KHTA precipitation during fermentation as the alcohol comes up and we're fermenting cold. And let's say that's going to drop the pH about 0.15, so we're at 3.33, right in the middle of that desirable range that I'm showing by the yellow oval there, the whole range being about 3.2 to 3.45. And then the TA will come down about a gram per liter, so now we're at 7.2 and we're closing in on our target. Next thing, when we cold stabilize before bottling, the pH is going to go down another 0.05. So now we're at 3.28 and the TA is down to 6.7. So we're a little bit too low. And now how are we going to correct that acidity, tweak the tail to bring it up to 7.0 without creating a tartrate instability? And the answer is we're going to use the weak acid that's stable at low pH. We're going to use malic acid, and we're going to add 0.3 grams per liter, and that'll take our TA up to 7, and it will also drop our pH to 3.25. This has the added benefit that as we're moving the pH down just a little bit, we're decreasing, as you can see right here, the curve is almost up and down. And so a little tiny change in the pH lowers the bitartrate concentration considerably, maybe 10%. And that can confer some added cold stability to the wine. I've had wines that I did this to that ended up getting stuck in a blizzard in the Rockies, and they were the only wines in the truck that did not precipitate. All right, so next we're going to make a fat, generous Napa-style Chardonnay with malolactic. So there's our target, 3.45 and a TA of 6.25, let us say. How are we going to get there? Well, first of all, we're going to adjust the must to 3.45. Then we're going to get our malate consumption, which will have the same effect as the Sauvignon Blanc, taking the pH up a little bit and the TA down a little bit. Then the KHTA precipitation is going to drop us back down 0.15 to 3.3, just as before, and the TA drops to 7.2. So far, everything is the same as the Sauvignon Blanc, but then we get our malolactic, which we've suppressed in the Sauvignon Blanc. We'll talk later on about how to do that. That'll cause the pH to rise about 0.15 to around 3.8 with a TA of about 6.2. Now, that might be a perfect spot. We have two options here. One is to use something to prevent cold stabilization and maintain the potassium, and that's called potassium polyaspartame, that we just pitch in at 200 parts per million into the wine, and it gets to be stable that way without refrigeration. This is really handy if you're a small winery or a home winemaker and you don't have the chilling capacity. It also retains potassium, which has some good flavor effects. There's a paper in your syllabus on page 273 that you might want to read that explains the sensory study we did that showed that higher potassium enhances body and flavor persistence in the finish of the wine. So we might like that. On the other hand, maybe we feel like we'd like to have a little less acidity than 6.2 in this particular wine. Then we can cold stabilize, and that'll drop the pH and drop the TA as well. So we have some flexibility there. Let's move on to red wines. Let's start with a low-tannin red. I've chosen Pinot Noir here, and we're going to shoot for pH 3.70 and a TA of 6.0. It's a relatively high TA for a red wine, but it's okay to bring a little more saliva into the mouth because Pinot Noir doesn't have very much tannin, and so it doesn't tend to be coarse. Other examples would be Saint Laurent, which has very soft and rogue tannins, or Nouveau Beaujolais. So how are we going to get there? Well, we're going to start by adjusting the must to 3.45. Now what happens? Well, first of all, we get that malate consumption that has the same effect. So now we're going from 3.45 to 3.48 with a TA dropping a little bit. Now we have our fermentation precipitation, which would take the pH down to 3.3 and the TA down to about 7.2, but simultaneously we have skin contact happening. And that's going to take the pH up by about the same amount. So now we're back to pH 3.48, but now the malolactic is going to raise it about 0.2. So at the end of that drill, we've got 3.68, and our TA is down to about 6.2, so we're very close to where we want to be. And then there'll be a little bit of pH-TA precipitation in the barrel. That'll drop us a little bit, so the pH ends up at 3.7, and the TA is about 6.0. Exactly what we were looking for. So once again, we just have to start off by adjusting the pH to 3.45 in the juice stage. This is immediately after we crush, before skin contact has occurred. So now, in the case of your big tannic monsters, your Cabernet Sauvignon, your Syrah, here we're going to go for a higher pH and a lower TA. A couple of reasons. We want that pH to be higher because then the oxygen appetite of the wine, which is brought about by a reaction called the vicinal diphenol cascade that we'll study in section 4, has the effect of gobbling up oxygen and protecting the wine from acetobacter and oxidation. We want the TA to be low because we got a lot of tannin here and we don't want it to be coarse. So we would like the minimum amount of acidity and salivary protein to come into the mouth. So that's why we have that as a target. How are we going to get there? Well, we've got to consider that there are some things that are different about this very ripe fruit. Generally speaking, Cabernet Sauvignon will come in with lower TAs, maybe 7.3 instead of 8.5, even after acid adjustment. And then lower malic acid because it's riper, and higher potassium. These are typical characteristics of ripe Cabernet Sauvignon. So, do we adjust to 3.45? No, not really. We're going to hedge our bets here, see what happens after skin contact. Because a lot of times we have some raisins and we want to soak out so that we get a correct Brix, be able to predict our alcohol content and maybe add some water. Then the pH will want to get adjusted to about 3.6. So this is after 24 hours of skin contact. And fermentation starts, we get that malate consumption that will take the pH up about 0.2 to call it 3.62, and the TA down around 0.3, not very much, too. So now we're at 7.0. We're in the middle of fermentation. We're going to get some precipitation, not as much during fermentation because the fermentation will be hotter. So I'm just going to talk about what will be the eventual total change due to KHT precipitation, some of which will happen in tank, some of which will happen in the cellar. We generally don't actually cold stabilize these wines, but they do get stabilized down to cellar temperature at least. And so we would anticipate overall that the pH would go down about 0.15 and we'd end up with a pH of 3.78. And TA down 1.5 to the range of 5.5 grams per liter. So then we get our malolactic, but we don't have that much malic acid, so we don't expect a big effect. Let's say the pH goes up 0.12, so now we've got 390, and the TA goes down 0.8, so now we're at 4.7. So now we're actually overshooting. We've got a pH that's higher than what we want and a TA that's lower than our target. So here's where the magic comes in, and this is a little trick I learned from Pascal Ribeiro-Gayon, who was the director of the Faculty of Enology at the University of Bordeaux. He showed me a wine like this, and he said, "Isn't this great? These are perfect numbers." And I said, "What are you talking about? They're crazy." And he says, "Well, no, they're going to self-correct in the cellar. So what happens when we're at 3.9 or 3.95 is that we get oxidation of sulfite in the barrel." And we're going to study this reaction a lot more in the next section, but the bottom line is that we create sulfuric acid, which is a strong acid, and that in this case would take the pH. So now we're at 3.85 where we want to be, with only a small rise in TA to 5.2 or so. Close enough to our target, and gives us a wine that can be supple and elegant without coarse tannin, and the ability to take care of itself in the barrel and in the bottle and be quite age-worthy. It also, I want to remind you, gives the Cabernet this phenolic floor that's characteristic of Bordeaux and Bordeaux-like wines like Chianti and Rioja, kind of an appetizing bitterness that is the flavor of sulfate. And I guess it's as good a time as any to tell you it's sulfate we're talking about, which comes from H2SO4, sulfuric acid, not sulfite, which is one of the three free SO2 moieties. All right, so let's just review here a little bit. We've determined that we've got these two desirable zones for making white wine at low pH and red wine at high pH. Here's another example where we might have an off-dry Riesling, so we got a little sugar in there. We might want the TA to be a little higher, and so our target would be 320 and 7.5 grams per liter. We really don't want to get too much lower than 3.20 because the molecular form that we can smell of SO2 becomes an important fraction. And that's why German Rieslings that really don't have very much SO2 still smell very badly of SO2 aroma. It's very difficult to manage free SO2 down below 3.2. So that's why we like to stay out of that low pH range. Here's our Chardonnay. My favorite wine and food writer for the Wine and Food Companion, Josh Wesson, who also wrote Red Wine with Fish. I just think he's a genius. And he wrote this article one time called Big Fat Mamas Can't Dance. And it was all about how everybody thinks that these big, fat, buttery Chardonnays don't go well with food. He says, well, actually, here's the formula. You want to have some kind of protein. It can be trout, it can be steak, but it needs to be lean. without a lot of fat on it. Grilled, low in salt, because that tends to exacerbate the high alcohol of these wines, and with a touch of sweetness. A little bit of mango chutney or raspberry vinaigrette just makes a seamless match, and I've done this many times. It's a great wine and food cooking tip. I don't particularly like this style of Chardonnay. I like the ones that taste like Chardonnay grapes, but I know a lot of people do, and that's how you prepare a meal to go with it. Then, as we said, we have our Pinot Noir at 3.7 with a TA that's a little high for most reds. And then down here, the big bad Cabernet with a high pH and low TA. And I think the whole thing is just kind of a beautiful natural dance that all these elements participate in. All we have to do, read our pH at harvest and make an adjustment, almost always with tartaric acid, to 3.45.